Your LTR model can fail even when the features look good. Query-level normalization makes BM25 vector and click signals comparable before LightGBM learns the ranking. After this, you'll understand how to assemble a pipeline that z-scores each query's BM25 vector, freshness, and click features for dependable LambdaMART signals. I'm Professor Pi, teaching search and IR with simple Python. Search features arrive from different places and they don't share a common scale. BM25 can be huge for some queries. Vector similarities live in a totally different range. Freshness and click counts are another scale again. If you hand that mix straight to LightGBM LGBMRanker, the model will chase the loudest numbers, not the true per-query relevance. What we want is consistent scores inside each query, so rankings reflect relative relevance, not which query happens to have larger raw values. Query-level feature normalization means rescaling every feature inside its query group so they behave similarly. Practically, we center and scale each query's features to zero mean and roughly unit variance. That prevents BM25 from drowning out click counts on specific queries and helps LambdaMART learn the ordering within each query. The trade-off is obvious. You lose cross-query magnitude information, so keep the raw features too, if that global scale matters later. We'll build a compact pipeline, inspect per-query drift, apply per-query z-score normalization for BM25, vector, freshness, and clicks. Train LightGBM on both raw and normalized inputs, then compare the re-ranked top documents against a relevance cutoff. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need a tiny toy dataset that exposes the problem in plain sight before we try to fix it. First, we assemble a toy query document table to inspect BM25 spread across queries. This snippet assembles a toy query document table and spotlights BM25 spread drift across queries. Why check this early? Because global feature summaries can hide extreme per-query skews. We build a pandas data frame named data with BM25, vector, freshness, clicks, and label columns so we can scan values quickly. Then a group by on query ID compares per query STD against the global STD. And the printed BM25 global STD versus query mean STD makes it obvious when a single query stretches the scale. Seeing those numbers side by side motivates the per query fix. Now, we normalize each feature inside its query so the model sees comparable values. This example applies per query z-score normalization to BM25, vector, freshness, and clicks columns. What problem does this solve? It removes the mismatched magnitudes that otherwise lure LambdaMART into favoring certain queries. We list feature calls, so it's explicit which features get scaled. And z-score wraps the mean variance math with a safeguard for zero variance groups. The group by query ID transform call writes normalized columns back into data in the original document order. Norm calls collects the new fields, and a quick mean check confirms they sit near zero for each query. The mean query bias shows that per query drift has been removed. Before trusting the normalized data, measure how LightGBM behaves when trained on raw inputs to get a baseline. This code trains a LightGBM LGBMRanker on raw features to profile baseline bias. What question are we asking here? We want to see how LightGBM reacts when the feature matrix still contains mismatched scales. Raw calls grabs the unnormalized feature columns, and we feed them plus labels into LGBMRanker with the LambdaRank objective. so LightGBM optimizes a query-aware, pairwise loss. The group list preserves query boundaries, mirroring how real logs are batched for LambdaMART. After fit, score raw is appended to data to capture the model margins per document, and the raw score bias print shows how much the mean score shifts across queries without scaling. Now, retrain with the normalized inputs and compare how much cross-query score drift drops. This snippet retrains LightGBM using normalized inputs to dampen query-level score drift. What decision does this step test? We want to know whether feeding per-query z-scores actually tames the cross-query intercept wobble. xnorm picks the normalized columns, and we reuse the same group structure, so LightGBM still respects query boundaries while optimizing LambdaRank. We also set num leaves conservatively to match the tighter feature scale. Larger trees could overfit tiny z-score quirks, while much smaller trees might underfit. After training, score norm stores the new predictions, and bias reduction compares that to bias raw. The number tells you how much cross-query drift normalization removed. Finally, produce a re-ranked view and check whether the normalized model changes the top picks in a useful way. This example generates the final re-ranked view from LightGBM normalized predictions. What remains to verify? Whether the normalized scores actually change which document wins for each query. A chained sort values, then group by first, creates re-ranked, a compact table of top-ranked docs with labels and scores. From that frame, we build top docs as an easy-to-audit map from query IDs to winning doc IDs, and success rate measures how often those winners meet our relevance threshold of 2 or better. If you raise the cutoff, success rate falls but isolates very confident wins. Lowering it broadens coverage. The printed top docs dictionary and high relevance rate summarize the baseline ranking you can inspect or compare further. In a real pipeline, you'd swap in your search logs and keep both raw and normalized pipelines for A/B testing. The same per-query z-score transform can run during feature engineering or inside a light feature store step before training. Those printouts and the top docs table are useful audits to see whether normalization stabilizes model behavior or actually shifts business metrics. Recap: query-level normalization rescales features inside each query, so BM25, vector, freshness, and clicks are comparable. Use it when per-query scale differences push your ranking model to focus on magnitude instead of relative relevance. One caveat: you remove global scale information, so preserve raw features if that signal matters. Next step: tune a BM25, K1, and B pair on the same pipeline, so your text signal and normalization play well together. Small tweaks there can change how much BM25 relies on per-query scaling. If short, practical IR helps, subscribe and watch the IR videos.